So as you saw, some of our zeros actually appear more than once. So we can have that happen. So really, like when you do a graph or anything else, we talk about zeros. We really only talk about the 1 0, but having multiple zeros at the same point, it's called multiplicity, and it does have an effect on the graph. Sorry, something's in the way here. So if I have something like this, like I said, we know that the zeros are going to be x is equal to 2 and x is equal to -2. However, one, the 0 appears twice. So although it appears twice, we'll only run it one time. But when you look at the graph, as we'll see here in a moment, that has an effect on what's going to happen. So if r is a 0, so I mean we have something that looks like x minus r, so then r is going to be the 0. So if r is a 0 of even multiplicity, then the graph is going to come down and touch the x-axis and turn around at r. If r is a 0 and of odd multiplicity, then we're going to cross the x-axis at r. So one touches and one crosses. So regardless of whether the multiplicity of a 0 is even or odd, the graph tends to flatten out near zeros with multiplicity greater than 1. So let me go into decimal. We'll give you a demonstration. We see here I have fx equal to x minus 3 times x plus 4. So we have a 0 here and here. So my 0 r, we have one at x equals 3, and then we have one at x equals -4. We see right here, got a power of 1. So it kind of acts like a linear equation here, and it just crosses at those points. Let me use some red so you can see that a little better. We just cross. Now we're going to change one of these. What we're going to do is we're going to take the 0 at 3. And now instead of having x minus 3 times x plus 4, we're going to have x minus 3 squared. So we see what happens is my graph makes a change. So here we have a multiplicity. There we go. Multiplicity of 1 at the -4. We see right here, and we cross. However, now that 3, because we got that power of 2 on it, this is going to be a multiplicity of 2. So we see what happens here is that we come down, we touch, and we turn away. So here we touch at 3, we cross at -4. So what we have here is behavior that we saw when we were talking about end behavior, is that when we had a odd power, then we act like a cubic. So when we had odd powers, we saw this. Our graph would come up across x-axis and keep going. So we're kind of seeing a similar thing here. When we have an even power, what we would see is your graph would come, touch, and turn away. So we're just getting that same phenomenon again. So when you have even multiplicities, you come down and touch and turn away, just like if you were looking at an even power function. And if it's odd, you cross at that 0, just like if it was a odd power function. So just play with this just a little bit more. So let's go back and play with that -4 now. So originally we had a multiplicity of 1, so let's change it, and we're going to have a multiplicity. We're going to have a power of 3. So now we see right here, that same one, we still come down and we just touch here. We touch at 3 because we had an even multiplicity, and we still cross here because we have an odd multiplicity. The difference is how we cross. So here, instead of being like a straight line going through, we came up and we flattened and turned. So that's one of the things here is that once those powers go up, so we'll take that x minus 3 to the power 2. If I change that to a power of 4, you see that kind of flattens a little bit there. If I change it to a power of 10, you see it really flattens. If we make this a even power of 11, we see it flattens more. So as you see, both of those with high multiplicities get really flat. So as the multiplicity increases, what's going to happen is your graph will flatten at those spots as well. But we can use this information to make rough sketches of our graph. So here we have -4 times x plus 1/2 squared times x minus 5 cubed. And we want to find the zeros of this function and the multiplicities of each zero. Then we're going to state whether we expect the graph to cross at the x-axis or touch at the axis and turn back around. So if we take that, we want to look at f of x is equal to 0 to find our zeros. So that means we got -4 times x plus 1/2 squared x minus 5 cubed equals 0. So we don't have to worry about this -4 here because there's nothing that's going to make that -4 0, so that has no effect on zeros. What we need to be concerned with is these factors right here. So it doesn't matter what the multiplicity is, because if I broke that down, I'm just going to have an x plus 2 and an x plus 2 like we saw earlier. Or sorry, an x plus 1/2 and x plus 1/2 like we saw earlier with the x minus 2, I believe it was. We just need to look at this part and figure out when it is equal to 0. So we have a 0 at x equals 1/2. In here, we just have to look at the x minus 5, assuming that's going to equal 0, and that's going to happen when x is 5. So I have two zeros, and I'm going to have their multiplicities over here. So my zeros are going to be at -1/2 and at 5. So for the -1/2, we look at the factor, it has a power of 2, so the multiplicity is 2. And if we look at the -5, that came from the factor of x minus 5, which had a power of 3, so it has a multiplicity of 3. So when we look at the behavior at the 0, what we're going to see here is that because this is even, we are going to touch and turn away. And because this is odd, we are going to cross at that point. If you're going to make a rough sketch of this, we know we have a 0 over 1, 2, 3, 1, 2, 3, 4, 5. Not to scale, I'm sorry. This will be my -1/2 here, and this will be my 5 down here. What we know is that at this point, because we touch, we expect that we're just going to come up, touch there, turn away, and then we come up to that 5. Because of that odd multiplicity, we expect we'll come up to that point, and then we're going to cross. We just have another question here. It's like, is it going to come at it like this? Or does it actually come from above, touch, and then cross here? So we'll worry about the rough sketches of the graphs here in a little bit. Right now, all I want you to do is just take these functions here, so a and b, and find their zeros and their multiplicities and determine whether the graph is going to cross or touch at the x-axis at each of these zeros. All right, so for A, we see that is equal to 0, then everything with an x, every factor with an x is what we have to look at. This is saying that when is x equals 0, well, it's 0. When is x minus 2 equal to 0? And when is x minus 3 equal to 0? So if we go back and we find our zeros, so I'm just going to write for multiplicity, and then behavior for the behavior is 0. We don't have to add everything here. What we see is that this is going to get a 0 at 0 here, and it has a power of 2 on it, so its multiplicity is 2. And because your multiplicity is even, it should just touch. Pick another color for the next one. If we look at this factor here, x minus 2 to the power of 3, well, then my 0 would end up being just 2, because if x is 2, 2 minus 2 will be 0. And it has a power of 3, because your multiplicity is odd, we expect to cross at that point. And then the x minus 3, so just remember that always has an invisible 1 on it. So x minus 3 equals 0 only when x is 3, but this multiplicity is this invisible 1 on it, and that's an odd multiplicity as well, so we are going to cross. The next one, we have a couple more zeros here. If we go through here, we got this minus out front, which we don't have to worry about. We just have to worry about any of my factors with an x. So we got x minus 1. We want to know when that equals 0, because my polynomial is supposed to be equaling 0. So that is when x equals 1. Then we have x plus 1. What does that equal 0? Well, that equals 0 when x is equal to negative 1. And then we have x plus 2. That equals 0 when x is equal to negative 2. And then we have x plus 3, which will equal 0 when x is equal to negative 3. So we want our 0, our multiplicity, and our behavior. So my first 0, I got a 0 at 1, and the multiplicity on that factor is 5, which is odd, so we expect to cross again. So for the next one, we got x minus 1. My 0 at minus 1 came from this factor, which is a power of 3, which is also odd, so we expect to cross again. So x plus 2, that gave us the factor, or sorry, that was my factor, which gives me the 0 of negative 2. Negative 2 comes from a factor that had a power of 2. So negative 2 has a multiplicity of 2, which is even, so we touch. And the last one, we got the x plus 3. So that means my 0 is going to be negative 3. And the multiplicity is that invisible 1 again. So we know we got a multiplicity of 1, which once again is odd, so we cross. Turning points. When we talk about turning points, if I look at a polynomial, oops. When we're talking about turning points, all we're really talking about is really your minimums and your maximums. So in general, if a polynomial, or if f is a polynomial with a degree of n, then the graph of f has at most n minus 1 turning points. Which tells us a lot in your quadratic equations. Quadratics have a degree of 2. But all your quadratics always give you a graph like this. So we only have one turning point. So remember, we're saying at most n minus 1 turning points, because that is the most we can have. We could have less than that with any kind of polynomial. So as an example here, I have this function, which is 4x minus 3x squared minus 2x plus 4. We have a degree of 4, and we have 1, 2, 3 turning points. If we look at our other graph here, this is x squared minus 3x, or sorry, minus x cubed plus 3x squared minus 2x plus 1. This one is also degree 4, but we only have 1 turning point. So really all this is telling us is the maximum amount of turning points I can have. It's always going to be the degree minus 1, but I could definitely have less turning points than that. So knowing your turning points can help you a little bit in graphing because it'll tell you if you've gone wrong. So we're going to use the leading coefficient test to determine end behavior when we're first going to start graphing functions. So we're going to use end behavior. Then we're going to look at the x-intercepts. We're going to look at those zeros. Oops. Bring that back. Then we're going to look at x-intercepts or zeros. And we are going to basically completely factorize your f of x so we can find those zeros. Then we can find zeros and multiplicities. Once we have zeros and their multiplicities, we have these factors of this form here. We know if our multiplicity is even, then we are going to touch the graph at that 0. If my multiplicity is odd, I know I'm going to cross the graph there. I know that if my multiplicity is greater than 1, that's going to start flattening more and more and more the greater it gets at those zeros. So it's just some basic stuff that helps me get an idea of what the graph should look like. We're going to find our y-intercept by computing f equals 0. We're going to skip symmetry for now because most of these graphs are not going to be symmetric anyway. And then we're going to use the fact that the maximum number of turning points is n minus 1. So this is a way to check if we've graphed everything correctly. So if we have more turning points than n minus 1, we know we made some sort of mistake. So if we have fx is equal to 2 times x plus 2 squared times x minus 3. We already have this completely factored for us. So this 2 isn't going to be too helpful for us. So we're going to ignore that for now. And what we're going to look for is my end behavior. Or sorry. Actually, 2 is a little helpful because I need from end behavior. I'm going to look for my zeros first. My zeros are going to be x equals negative 2 with a multiplicity of 2. So we know we are going to just put at x equals negative 2. So that's one thing that we know is going to happen. And my other 0 is going to be x equals positive 3 with a multiplicity of that invisible 1. So in this case, we know we are going to cross at x equals 3. We know that we're going to have a 0 here and here. And we know that we're going to bounce at the 1 at negative 2, and we're going to cross the 1 at 3. The problem is do I come at 2 from this direction? Or do I come at 2 from this direction? That's when end behavior comes in. So if we think about end behavior, remember What we did last time is that if we had something that was completely factored when I wanted the end behavior, I said take like the leading coefficient, or you're sorry, your leading coefficient, your like leading term in each factor. So this is a factor, the leading term is just 2. X plus 2 is a factor, that leading term is going to be x. And we're going to keep that power on it because we get x 2 times. Here we have a x, again, it's my leading term, and the power on that is going to be 1. So we're going to keep the leading term and their powers. Because what this is telling me is that when I get my leading term, what I had to do was I had to multiply that 2 to that x, to the x in the next factor, and then this x as well. So I should have 3 x's. So 2x cubed is my leading term. So my end behavior should be a cubic. And we got a positive coefficient, so it should be opening like this. Okay. Turning points. Because we got my leading coefficient, I know that my degree is going to be 3. So I should have at most 2 turning points. If I have more than that, I made a mistake. And another point you should always look for, just to kind of help you, sometimes it's not very useful, sometimes it is, look for your y-intercept. So y-intercept is going to happen when f is equal to 0. So I have 2 times 0 plus 2 squared times 0 minus 3. So that's going to be 2 times 2 squared times negative 3. Or it's going to be 8 times negative 3 or negative 24. So it's going to tell you that this is supposed to be way off the map, way off of here. So it gives you a better idea of how this should be graphed. So I'm going to move everything just a little bit. All right, 2 things in the same place. So this is not going to be the scale. Just trying to give ourselves a little help here. So we expect that this is probably about negative 20. So maybe here's about negative 24. So that's where I should be crossing at. So, information we have. We know we have a 0 here. We know we have a 0 here. And we know we crossed the y-intercept here. We know from end behavior that how this should start is that we come up this direction to hit this point. So we're coming up from here and we exit like this. So it gives me an idea. So we said we touch at negative 2. So we come up, we touch, we turn away. And then I know I have to cross at this point down here. So I'm actually going to redo this part just to make it a little smoother. Come up, touch, do the best you can, turn back. And then we know we cross through here. Let's see if I can smooth that out just a little bit. So we come up because of end behavior. We turn here because that is a touch because of multiplicity at 2. We have a intercept here on the y-axis. We come up through here. Sorry, it keeps wiggling when I try to graph this. That's vaguely what that graph should look like. So we can always go see if that's what it should look like. So here I graphed it. So we did. We came up. We touched here at that negative 2. And then we turn back around and then we cross the x-axis at negative 24. We keep going, we turn back around, and then we come up and we touch here at the 3. And we have 2 turning points, which is the maximum I said I could have. So for this one here, you want to do the same thing. You want to get a graph of it. So you need to have your y-intercept, x-intercept, and multiplicities. And you need to know end behavior. So those are like the big things you need. Anything else is a little bit of extra. You could look for the turning points just to kind of, like I said, to double check on things, but this is essentially the big three that we need to have. Intercepts, behavior at the intercepts, and behavior. Right, so hopefully take a moment for this. Behavior. So we have an x squared. We have this x, and it has a multiplicity of 3. And then we have this x, and we have a multiplicity of 1 on that. So it's that leading term of each one of your factors and the powers. So if we multiply those together, we are going to get x to the power of 6. So what you have here is you have a positive coefficient of 1 and an even power. So we should be expecting an end behavior like this. So it should act like a act like a parabola that is opening up. So we'll do this one because it'll be easier. Y-intercept. So this always happens when x is 0. So g of 0 is going to be 0 squared x minus, 0 minus 2 cubed times 0 minus 3. So this 0 out front is going to just basically make this 0. Now if we look for x-intercepts, also known as our zeros, we're also going to need, let me make a little space for this, the multiplicities and the behavior at these spots. So we'll write the multiplicity, and then we're going to write how it's going to behave at the 0. So here, let me erase this. This is giving me a 0. Color code is easier to see. This says I have a 0 at 0 because we're looking at x equals 0. So that means we have a 0, 0, and a multiplicity of 2. So we expect to touch at this spot. So for my next one here, if we look at that factor, then we're gaining x minus 2 is equal to 0, meaning that x would have to be positive 2, and our multiplicity is 3. So we're going to cross at this point. And then for our last one here, we got x minus 3 equals 0. That means that my 0 will have to be positive 3. And we have that invisible power of 1, so multiplicity of 1, so we are going to cross again. So notice that got 1 here, so we should cross like a line here. And because we got a power of 3, we should flatten a little. Basically, we're going to look more like a cubic at that point. Okay, let's take everything that I have here. So I know I have a 0 here, which is also my y-intercept. So my y-intercept and x-intercept are at the same place. So we don't have to worry about another point there for the y-intercept. Then we have a 0 at 2 and a 0 at 3. And we know end behavior is at the endpoints of this function here. We should be going up at this end, going up at that end. So if that's true, what's going to happen here, I'm going to pick a new color, is I'm going to come at this 0, which has a multiplicity of 2, so I'm going to touch. So I come down and I touch and I turn away. I'm going to have to turn away and come back because I'm supposed to hit here at this 2. So a 0 at 2 had a multiplicity of 3, so we're going to cross. But remember, we need to flatten a little bit there. So we're going to come in like that. Then I have to turn back around again because I have to hit the 0 at 3, which is multiplicity 1, and I cross that one more like a straight line. Try and get rid of the red. This is vaguely an idea of what that graph would look like. If we were to look at the graph, that's what we see. We come down, we touch here, we turn around, we flattened a little bit at 2, and then we came back and crossed to 3. Like I said, this is vaguely an idea of what that graph should look like. And this had a had a degree of 6, and we have 1, 2, 3, 4 turning points. So we still have less than 5 turning points. All right, I'm gonna try this one more time. It's nice to have a vague idea what graphs look like while practicing this. So now we're going to have a negative out front, so negative x minus 1 to the power of 5, x plus 1 to the power of 3, x plus 2 to the power of 2, and x plus 3. Once again, you need end behavior, the zeros, and their behavior at the zeros, or their multiplicity, and you need to know your y-intercept. And like I said, as a bonus, you could look at turning points just as a way to check it. So if we look at end behavior, we're going to treat this this is just a -1 out here. So we need to take that -1, which has no power on it. We need this x, and its factor had a power of 5. We need this 3, and that factor had a power of 3. We need this x, and its factor had a power of 2, and we need this x, and its factor had a power of 1. So I'm getting a leading term, like I said, without having to FOIL this whole thing, or distribute or expand. We're going to get a leading term that is going to be negative x to the 5, 6, 7, 8, 9, 10, 11. So it's a odd power. So that means we're going to get one of these sneaky curve things going on, or cubic curves. The question is, though, is it this one or this one? But because we got that negative, we're looking at this curve. So my end behavior should look like this. So y-intercept, that's one x is 0. So we have negative 0 minus 1 to the power of 5, 0 plus 1 to the power of 3, 0 plus 2 to the power of 2, 0 plus 3. We're going to have a negative 1 to the power of 5, 1 to the power of 3, 2 to the power of 2, and 3. So a negative, so -5, or -1 to the power of 5 will just be -1. 1 to the power of 3 will just be 1. 2 to the power of 2 will be 4. And then we have that 3. So what we're going to have is 12. So we just have to just expand this just a little bit. There we go. 11, 12. Let's do zeros and multiplicities next. So I'm going to write down each factor. So what we have is we don't care about this one. We care about the part with the x's for the factor. So we have an x minus 1 to the power of 5. Meaning my 0 is the positive 1. My 5 is the multiplicity. So my behavior is I'm going to cross because it's an odd multiplicity. I have x plus 3, or x plus 1, sorry, to the power of 3. So my 0 would have to be the -1 to make this equal to 0. The multiplicity is 3. And once again, we're going to cross. Then I have x plus 2 to the power of 2. So we have a 0 at -2 with a multiplicity 2. And we are going to touch at this point. And then we have an x plus 3 to a power of invisible 1. So 0 isn't -3. The multiplicity is 1. And we are going to cross. So the crosses, remember, this is a multiplicity 1. So this is going to be more like a straight line. This is going to flatten because that multiplicity is 3. And at multiplicity 4, we should flatten more. And once again, we have a degree is 11. So at most 10 turning points. We're not going to have that many. All right, let's start labeling everything. So we know that we should have a 0 at 1, 1 at -1, 1 at -2, 1 at -3. A little better. And we're supposed to cross our y-intercept way up here. So this is going to be a tight graph. We know end behavior, it should look like this. So when I'm at the ends of my zeros, I'm expecting this kind of behavior. So -3 had a power 1, so I expect to come at that and just cross. And then when I come up to -2, that had a multiplicity 2, so I expect to come around, touch, turn away. Then I have to turn around again and come at the -1, which had a multiplicity of 3. So I should come back and I kind of flatten through there. So touch, turn away, come back, flatten. Then I have to go all the way up here. Touch, turn back, and then I have to have another 0 here at 1. And this one is going to be another cross, but my multiplicity of 5. So what I expect is I'm going to come down and I really flatten out there. Okay, I'm going to do a little cheating here to make this just a little easier to see. Technically, I shouldn't do this. Because it's not really flat there, or a straight line. I'm going to use it to help me get the line straighter. And then we're supposed to really flatten out here. Oops, just trying to get rid of the red part. So that is vaguely what that graph should look like. We see we get that similar thing. We cross at that -3, come down. So this one had just really came down very far. We come up and we touch at 2, then we flatten -1 and cross, come up, touch at 12, come on and flatten at 1. So let me just bring this part just a little closer to see. So we can see that flattening effect there.